Hi, today's topic is structural induction, which is more general concept of induction, which can be used for the recursive definitions, recursive function, recursive set, and any other interesting application. Before starting this, I'm going to review last class recursion. So we have seen these recursive definitions of functions. So we can define natural number using recursion. We can define um, power 2 using recursion, and also we can use we can define factorial using recursion. And there is another recursive definition, so we can define summation and product using um, the notations. And one of the famous example is Fibonacci numbers, which use two previous number, actually one step forward, one step previous and two step previous, and summing them together is current Fibonacci number. So we have checked the um, upper and lower bound of Fibonacci. Upper bound is 2 to the nth. So we have seen this is correct or not. So we can simply define this inequality for the upper bound. So check the base case first and find inductive hypothesis. That is, this is based on strong induction. So that's why we need these. P of j is true for every integer j from starting point 0 to current k. So that's then we need to show p of k plus 1 is true, and p of k plus 1 is this because of the definition. So we have two k's, k plus 1 is 1, and k plus 1 is greater than or equal to 2. K plus 1 is 1 is easy. Definitely this case is true. If that is greater than or equal to 2, we need to use definition to find k plus 1. This is the definition. So other side bound will be applied with that definition and inductive hypothesis. So this one is larger than that. We may think that another number like this is larger, and definitely. And in another way, we can rewrite this like this, and this will be like this. This one is same to this, so that's why this is true. Another lower bound. Lower bound is a little bit complicated because we need some special case 0 and 1. So that's why we didn't use that. Uh, so that's why we skip those two because we cannot use negative number here. So that's why we can start from 2. And so maybe if you have 2 current state, previous one will be 2 plus 1. So this is available. So that is 2, and other side is 2 to the halves. This is square root 2. This is smaller than 2, definitely. And so next step that we need to do, we need to prove when k is equal to 3 and greater than 3. And likewise, previous question, we have to use this definition. So this is the right side, and we can simplify this with smaller one. This previous we used larger one. So anyway, we can use that and rewrite this into this, and finally it will be this, and this is same to the original p of k plus 1. So that means p of k plus 1 is true. So yeah, we can use this recursive definition to define set. Okay, here we have the multiples of 2. So starting point is 0, and if x is in the set as, another member will be x plus 2. So we know about the 0, another member will be 2, next is 4, 6, 8, 10. Yeah, it's gone. And there will be exclusion rule to make sure the set, but it is usual for this recursive definition, so you can simply skip this. Yeah, here are some examples. The first one is an example with 2 variables. We know about 2 bases. Here 6 and 15. When we have x and y, that is a member of S, we can use x plus y to make another member. So 6 plus 15 is new, 21. We can make another this combination and this combination. And other thing is as multiple bases with multiple element in each base is 1 1 0 0 1 1. First we can make this with xyz for this alpha 0, and for this 0 alpha. Another one, if you have 2 members, we can make the element sum. So we have 1 1 0 0 1 1, whether it be 1 2 1. Now you can make other members using that rule. The last one is force of 3. It is 3 to the nth. So basis will be 1 because this is based on multiplication. If you have x, then another member 3x. 3x here, 9, 27. Okay. And we have this general form to define this set using recursive definition. We need base step, some specific elements are in S. Next one, recursive step, given some existing named element in S. Some new objects constructed from these named elements are also in S. Finally, we have exclusion rule. Every element in S follows from the basis steps and a finite number of recursive steps. So using it, we can define strings. There is a set, alphabet set, which is any finite set of characters, and there is string set sigma star of the alphabet sigma. So basis epsilon, the epsilon is empty string, is a member of the set sigma star. So we can use recursion. If W is a member of sigma star and A is a member of sigma, then WA is a member of sigma star. This is a string and followed by a character. You have some string A, B, C, and maybe if you put A after that, that is a string. Oh, 1, 2, 3. You can put 4 after that. Okay, this is not like 4. Yeah, 4. That was a string. And palindromes. This is another string that has this specific property. This string has same backward and forward. This arbor here and there, same THT, never old driven. Yep. Never odd or even. Okay, this is how to read. Anyway, this one backward also same. So how to define this? Epsilon, that is empty space, empty string is the palindrome. A is a palindrome for every A, and sigma. If P is a palindrome and A is the alphabet, then APA is palindrome. So you have empty string and put A or put B like this ever. So B, B. So now you can add A, because you always put same character in front of the end of the, so you will see backwards forward same. Okay, this is another thing. So you want to make a binary string which has no 1 before zeros. That is, this is not available. Maybe these or these, maybe these kind of things are available. So first you have empty string, and when you have x will make this ox ox1. So here you can make 0, 1. Yeah. Next time you can make o 1 1 again, 1 1. So yeah, it generates that specific binary string using the rule. Okay, and we have seen these functions, and I'm going to introduce one more thing. It's about the number of subspecific character. When you have C as character variable, this is number of characters C. So there's not empty string doesn't have any characters, so number of C will be 0. This one is W will be a string, and we have C as a character, so this will be 1. Yeah, we know there is a 1C. This will be 1, but we don't know about the string itself, but we can find number of string. So here, this one, W is string, A is character A, so that means A doesn't have any C. This will be 0. It become this. All right.